Good morning, everyone, and thank you very much to the organizers for allowing me to be here. For me, it's a pleasure to be here at ESO. So I'm going to talk about JPAS, this project, the Javalambre Physics of the Accelerating Universe Astrophysical Survey, which is, is going to be conducted from the Javalambre Observatory. Okay. Of course, I'm talking on behalf of the JPAS collaboration. I don't know if this is working. Okay, so this is the outline of my talk. I would like to start with a very brief scientific motivation for this project. Then I will tell you about the implementation of it, some precursors that we have been conducting at Javalambre in preparation for JPAS, and also I will to finish with the current status of the mission. Okay, so let's start with the scientific motivation. And it's good that I'm talking after this very nice talk by Guadalupe, because I don't have to enter in the details of cosmology. But JPAS is a cosmological project. The main goal is to do cosmology, and in particular, the main goal is to measure BAOs in order to understand how dark energy is playing a role in the universe, how the universe is expanding in an accelerated way. So I'm not entering the details because this has been explained and all of you know, but of course, if you want to measure BAOs with a typical scale of 150 megaparsec, it's obvious that you need to map a huge volume of the universe, or at least several times the typical size of these signatures, okay? So this is how the Javalambre Observatory is conceived. It's a new facility which is conceived for carrying out the large-scale surveys, okay? And the telescopes that we have in this observatory are optimized in terms of the ATNU. We want to optimize the aperture times the field of view times the time that we can dedicate to the survey, okay? So this was the final, let's say, definition. We are having two telescopes, the JST 250, Javalambre Survey Telescope with a field of view of 7 square degrees, okay? So it's a large ATNU telescope. And then the JST 80, which is the Auxiliary Survey Telescope, which is smaller, but still with a very nice field of view. And it was conceived for doing the preparation, but also very significant science in preparation for JPAS, okay? So this is one of the requirements. So we need to be able to observe a large field of view, but also then we need to observe a huge number of galaxies and measure distances for millions of galaxies. And this is important to measure accurate redshift determinations. So in this point is probably one of the most specific characteristics of Javalambre, of the JPAS, is the fact that we are using an alternative to classical spectroscopy. So instead of using classical spectroscopy to measure distances, to measure redshifts, we are using narrowband filters, okay? So which is something that is not completely new, but we are making this as a very unique case in our observatory. There is, of course, the feasibility to measure distances with narrowband filters. This is not new, as I did. This is already known from many previous projects. And essentially, what you are doing is you are doing images in different wavelength ranges that finally, when everything is put together, you can come up with a pseudospectrum, okay? So the goal of the JPAS is to observe 8,500 square degrees of the universe. This is a factor of 1,000 of the typical size of BAOs in about 7, let's say, let's be more generous, of up to 1 decade in the next years, okay? So the goal is to measure BAOs, as I was explaining before, and okay, the pointer doesn't work. Anyway, well, you can see the main goal is to try to reach the 0.3% accuracy that we expect to do for 100 million galaxies, and of course for other galaxies with probably lower quality, around 300 million galaxies, the accuracy will be around 1%. So this is the survey, the filters implementation. There's 54 narrowband filters from the blue to the red, which are complemented with 2 medium band filters at both sides of the optical spectrum and slow and I, okay? So this is essentially the filter set of JPAS, okay? But the point is that this is not only for cosmology. Cosmology is the main driver, but if you think in the type of data that we are going to gather, at the end, this is going to be useful for essentially most cases in astronomy. Why? Because we are getting a J spectrum, is the way that we say, a low resolution spectrum for essentially every pixel in the sky, okay? And this is very important for essentially all types of science that we want to do. And also it's very important to realize that because every observation is done independently from the other, at the end, the low frequency flux shape of this pseudo spectrum is very robust because you don't have the typical color terms that you have in classical spectroscopy using standard flux and things like that. Anyway, so this is the definition. This is the collaboration. This motivated the creation of a collaboration, the JPAS collaboration, essentially funded by Spain and Brazil, okay? So the funding agencies, you can find it there. The collaboration has more than 200 people from 45 institutions, 18 countries, and most of the funding is coming, I insist, from Spain, okay, from Aragon government and the Ministry of Science. And then the development of the instrumentation, well, you can see the observatory and the telescopes and the data center is coming essentially from Spain, and the instrumentation has been developed by Spain and by Brazil, okay? So let me show you just a fly over the observatory. This is Javalambre. This is 2,000 meters above the sea level. It's a very, Carlos already explained on Monday, it's one of the less populated areas in Spain, 3.5 inhabitants per square kilometer. And well, you can see the two main buildings for the two telescopes, plus well, the installations for dormitories and control room and everything which is needed in observatory. And also, it's one of the ICTS recognized as the Spanish Ministry of Science since 2014, like the Canarian observatories, Calar Alto, and other observatories, okay? It's a very dark site with excellent seeing conditions. You can see that we are in a very dark area in mainland Spain, northeast Teruel, in down there it will be Valencia, and we are reaching 22 magnitudes per square second, okay? In this is surface brightness in the sky, in the zenith, and then the seeing is around 0.7, okay? So it's a very interesting place for doing professional astronomy, as you can see, and it has a lot of possibilities. This is during the night, and also very interesting during the day. If you like cycling, probably you have seen that 6 weeks ago there was one of these stages of the Spanish Vuelta ending at the Javalambre observatory, okay? Okay, so this is the Javalambre survey telescope. This is a 2.5 meter with a field of view in diameter of 3 degrees. That of course corresponds to a very large focal plane of almost half a meter, okay? The main characteristics is the largest in view, of course. It's complex because we have an hexapod in M2 to do active optics, and also, I will explain later, an hexapod in the camera, okay? So the image quality that provides the telescope is very nice. The field of view is quite remarkable, and you can see the focal length is very fast telescopes, and f3.5. This is an example of an image taken with an interim camera, the Pathfinder camera, before the arrival of JPCam, which you can see an image of 0.4 seconds for this galaxy in comparison with the same galaxy as seen by ESO. This is JPCam. JPCam is a very complex mosaic of CCDs, 14 CCDs, large format CCDs developed by Teledyne, okay? The final ambient field of view of the camera is 3.4 square degrees after some bafflings, and after, of course, we cannot cover the entire focal plane with silicon. And well, it's more than 1,200 million pixels, so it's probably one of the largest astronomical cameras in the world. There is also an hexapod in the camera to do the active optics and guarantee the image quality during observations. And of course, it has a very low readout noise electronics that allow us to go, let's say, deeper than probably with other typical CCDs. This is another view of the camera, okay, the three subsystems. Well, you can see down here the camera system, the cryostat, the focal plane, the different detectors, and the image acquisition system. And then on the left, you have the arrangement, the flange, the interface with the telescope, with an hexapod actuator system that I insist, both the M2 and the camera can be controlled actively to guarantee the image quality. And then this system there is the filter and shutter unit, the shutter, which is a curtain-like shutter, okay, because the field of view is very large. And also there is the filter that are in filter trees. Okay, we have 5 filter trees, and this is what I'm going to explain. Well, these are the filters, the 56 filters now with the effective transmission, taking into account the quantum efficiency CD, the overall optics throughput, and of course the atmosphere at Javalambre. Okay, and you have and you can see there the filters. Well, the filter trace. We have 56 filters, but of course we don't want to populate each filter tray with only one type of filters, because otherwise it will be more money in filters rather than in the observatory. Okay, so what we do is we do some clever strategy to populate the filter trays with different filters, as you can see, in the sense that each CCD sees only one filter. Okay, and then you can change the filter trays during the observation. Okay, so this of course implies that you need to do some clever survey strategy. So let me just summarize how we work. Imagine that in a given filter tray, let's concentrate in one of the filters. Okay, so each pointing is a dithering of 2 by 2. Okay, so this is one pointing. We will continue mapping the universe. Okay, in this way, 2 by 2, and we will cover it. Okay, but of course, while doing this, all the CCDs are observing. So these are at the same time doing their own work for the 20th, for the 1st. So at the end, the point is that when you are covering the sky in this way, this, for instance, for this particular example of 4 by 2, this is the only region that is covered by all the filters. So you can imagine that actually with this configuration and only with these only few pointers, we won't have JPass data yet. So this is the meaning that you want to grow the survey from a seed, okay? And this is what is expressed in this the figure, which at the beginning of the survey, the first pointings, you get no JPass data. I mean, you don't get all the information, but only when you are growing from a seed, you are accumulating and you are finally getting, let's say, the area covered with the 56 filters. This took us to define 4 seeds to grow the survey. I'm not entering the details. These are the 2 areas that come up with the 8,500 square degrees, the different areas from which we are going to start. Okay, and these are the depths. Okay, finally the depths are, we are going to reach between 22 and 23 magnitudes in the narrow filters, and in ESO filter around 23.5 or even 24. Okay. So this is the expected outcome of JPass. So a huge amount of data, millions of raw images, 1 petabyte of data. And the most important thing is, of course, that we are providing photosheets for several 100 million galaxies, okay? Of course, this requires of a significant amount of storage capabilities and computing capabilities that there is in CEFCA, but I would like you to keep on the attention that it's not only for cosmology, it's not only for Redshift, but there is a huge amount of science that can be done, okay? That's going to be done because this is like working with an integrated field spectrograph of the whole sky. And all the data that we are going to acquire and provide is going to be provided in virtual observatory format, okay? Let me go very fast through the precursors of JPass. So I'm not entering the details of JPass because it was already presented by Carlos and there will be a talk on Friday by Alessandro, but this is an ongoing survey, which is already amounted to more than 4,500 square degrees and is taking very nice results with more than 30 papers in referred journals since 4 years ago, okay? Mini JPass, this is already the first JPass data because this is a small region of the sky that was observed a few years ago. It's 1 square degree. In the Aegis area with a full maximum of 0.8 arcseconds. And this was observed with an interim camera, not the final JPEG camera, but with the real JPass filters. And you can see here an example of the typical stars, quasars, and galaxies, that how the J spectra look. These are the depths that we are getting, okay, in this particular pointing from 22 to 24, okay. And these are some other additional example of the real spectra of JPass, okay, and how they compare with existing spectroscopic data, SLOAN or DESI, okay. So these are galaxies, quasars, and stars. Okay, so I just, because I'm running out of time, I'm just going to go through just want to explain that the type of science that we are doing. Of course, photosheets, this is the primary goal of the survey. In this first paper, we have already demonstrated that we are reaching the goal of 0.3% for around a third of the galaxies that we have observed. There is a new paper coming very soon in which we even improve this by combining the PDF probability distribution functions of JPass with the corresponding PDFs of broadband photometry. So it increases significantly, and it's something that's going to present in a few weeks. Milky Way stars, stellar atmospheric parameters. Well, you can see the comparisons. We are getting temperatures, gravities, and metallicities with values which are very close to the typical spectroscopy. IFU science, well, you can see that we can reach, this is a comparison of JPass data with respect to MANGA, spectroscopic data. You can see that we can retrieve very nice results. They compare it perfectly well, and these are the gradients, age gradients that we extend up to 2 effective ready. Galaxy evolution for 8,000 galaxies in mini JPass. Well, we are getting the same typical results of age gradients with, not gradients, of evolution with redshift, metallicity with redshift, and so on. Cluster of galaxies. This is detected, well, a good number of cluster galaxies detected with AMICO, okay, by Matteo Maturi. And of course, the impact of JPass of this J spectrum is that we double, we detect 100% more than with broadband filters, obviously, because of the resolution in a spectroscope. I finish. Current status. I just wanted to provide you with some flavors of the science that we are doing. So I finish here because we have started. Okay, this is actually the image that's going to be in a press release that we are going to send very, very soon. We have started. We have already observed the first 15 square degrees of JPass, and just this is a very nice view of one of these clusters that we have in this footprint. And just I show you with I leave you with the images, the J spectra of some of these nice galaxies, quasars, and stars. So sorry for the delay, for the time, and thank you very much. I can take questions if you want.